Hi class, welcome back. Today we're going to discuss inverse trig functions integration. This is from 5.7. A quick recap from last section is that we learned how to find the derivatives of inverse functions, inverse trig functions. So our goal now is to use the same rule to come up with a rule for integration. Now, obviously, we're not doing the integration of a inverse function. What we're saying here is we are sort of integrating a function that will give us a result of an inverse trig function. All right. So our goal is to integrate functions whose antiderivatives involve inverse trig functions. So it means the end result will be an inverse trig function. Use method of completing the square to integrate functions. Review basic integration rules involving elementary functions. So let's begin. Integrals involving inverse trig functions. The derivatives of the 6 inverse trig functions fall into 3 pairs. In each pair, the derivative of one function is the negative of the other. So like we said before, right? We only have to know one set of arcsines because we can always figure out the other one. It is just basically the opposite sign of it. So when listing the antiderivative that corresponds to each other of the inverse trig functions, you need to use only one member from each pair. So that's why we're going to summarize the integration into 3 categories. So the conventional use of arcsine of x of the antiderivative of this form rather than the negative arc cosine, because we know that we can always factor a negative whenever we need it. So these are the rules that we're going to be using, right? If we let u be a differentiable function of x and let a be a constant greater than 0. So what we're saying here is that if you have a function that is 1 over a square root of a squared minus u squared, then what we're saying is that the integral for this will be the arcsine u over a plus c. So now this is inside this arcsine. Similar argument, if you have now the integral of du over a square plus u square, this will equal 1 over a arctangent u over a plus c. And again, this is inside the tangent. Similar argument, if you have u times the square root of u squared minus a squared on your denominator, then this will be 1 over a arcsecant, the opposite value of u, over a, right, plus c. If you guys notice, it's always u over a, where u is the part of the function, right? This is the part of the function. This is where you have the x variable, the t variables. It's a function of some other variable, right? Anyways, all right, so let's go ahead and practice some of these. So in example 1, we have to choose which application we're going to be using, and let's see if we can match it to one of them. And it seems just like this one, right? It just seems just like this one. You have a square root, that's what calls my attention to pick one of these. Then I have a square minus another square, a square minus another square, right? So in this case, a will equal 2, right? Because you have 2 square. So a is 2. So when you use this rule, you know that you're going to have to use arcsine, and then you're going to be u over a. Well, u is the number being squared here, and a is the number being squared here. So it'll be x over 2. I always finish with plus c because this was in definite integral. All right, so again, it's just basically just picking one of these rules, right? Let's try the next one. The integral of this will be for 2 plus 9x squared. Let's see if we can match one of these. It seems like you need a square here and you need a square there. Well, technically, you can say this is a square, and technically you can write this as a square, right? The only thing here that we're missing is that we don't have the derivative of u needs to be present in here. So we're gonna use u substitution. So we're gonna say, okay, let u be 3x, du will be 3 dx. So we're sort of missing that 3 there, right? We're sort of missing that 3 in here. So we're going to go ahead and do that, right? We're going to multiply by 3 and divide by 3. Okay, so we took care of that 3, right? But let's talk about this part right here, because this needs to be a perfect square. So what we're doing here is we're just rewriting 2 in the form of a perfect square. How do we do that? Well, you can take the square root of it, but then square it, right? Because we know what happens there, right? It's like the square root and the square root will cancel each other out. So therefore, that's how we wrote it. To make it obvious to the reader that the square root of 2 will be your a value. All right. So we have everything we need. We know what a is. We know what u is. So we're going to do the following formula. We're going to have 1 over a, so that'll be 1 over the square root of 2 times the 1/3 that was in front of it, arctangent of, and then says u over a. U is 3x, a is the square root of 2, and then you finish with plus c. And that's pretty much it, right? So we're still doing u substitution. We're still using some of the rules here. Now we haven't talked about we haven't talked about one particular important concept that I was kind of holding off, but I'll mention it now. Notice that you cannot use any other rule. Nothing else will work here. Nothing else will work. None of the rules that we have defined before will work here so far. So we have now a new rule that allow us to take the integral of something that we couldn't do before. Think about that for a second. Because if you try to use u substitution here, right, in the first example, then you would have made this be u. But what does that mean? If you let u equal 4 minus x squared, then du would have been negative 2x dx. But obviously you would have needed an x on the denominator, which we don't. So u substitution does not work by itself, right? Because we needed something else. So we needed something else. So we can use u substitution, but now with the concept of an arctangent. Again, here, if you let u equal 2 plus 2, u equal 2 plus 9x squared, then your du would have been 18x dx. We don't have x dx on top. We don't have an x. That's too much. We can make up the 18, but we cannot make up the x. So that would have been it wouldn't work. But using u substitution along with the arctangent allows us to actually do this, right? Here you would use substitution u sub with power rule. This would have used u sub with power rule and it wouldn't work, or sorry, with natural log. So it wouldn't work, right? So now it's u substitution but with an additional rule, right, which is the inverse rule. Similar here, we're gonna do the same process. Notice that no other rule will work. I mean, you can try u substitution, but you cannot use power rule or natural log. So we're gonna compare this to this rule, right? So we're gonna have a perfect square minus a perfect square, and then we notice the base value of this perfect square is almost here, except that you're missing the 4, or sorry, that you're missing the 2. So what we're gonna do is we're gonna try to rewrite it by saying, okay, well, it is a perfect square. It is a perfect square. Let's rewrite it as a perfect square. That way, it makes it obvious what is your u and what's your a. Now, on the outside, you're missing a 2 there, but that's not a problem. We can multiply by 2 as long as we multiply the top by 2, right? And we can move this, and then this 2 will actually make sense because now this u will be part of your du, right? So actually, it worked out perfectly. Putting the to make up this 2, you make up this 2. And we're going to be using them both in two different directions, in two different places, right? So it's actually like recycling a number that you needed. So we're going to go ahead and do that. So now everything is perfect, right? We can even maybe rewrite this to help us visualize it. We're going to rewrite it as du on top, u on the bottom, and then u squared minus 3 squared. This will equal to, according to the rule, it says it will be 1 over a. So a is 3, so it'll be 1 over a times arc secant of the square of the absolute value of 2x, of your u, which is 2x, all over 3 over a plus c. So there you go. Now I gave you guys here 2 practice problems for you guys to try. Here are the answer there for you guys to check. All right. So we're going to continue with this. Sometimes it's not so obvious that you have to use one of these rules. Sometimes it's not so obvious. So we got to find a way to manipulate the algebra to make it so that we can actually use one of these rules. And one of these techniques will be completing the square. So completing the square helps us when quadratic functions are involved in the integrand. For example, x squared plus bx plus c can be written as a difference of 2 squares by adding and subtracting b over 2 squared, such as this form, right? Remember that completing the square, we do it by taking b divided by 2 and then squaring it, but we've got to compensate for adding it by subtracting it, and that gives us a perfect square here, and then this is just going to be outside this perfect square. So that's what we're going to be doing here. We're going to complete the square for this integral so that we can kind of see that we're going to be able to use one of these rules. Now remember that we cannot use u substitution and the natural log here, right? Doesn't make sense because we don't have, if we let u be the entire denominator, we know that du will be 2x minus 4. You don't have the 2x somewhere up here. That's why you cannot be using that one. So you have to use the u substitution in a different way. So let's try do that by completing the square for the denominator. So the 7 is going to be moved outside. We're going to work with these two. We're going to say, okay, x squared minus 4x, and we're going to add a number to make a perfect square. So how do we find this number? We take this number always, divide it by 2, and then square it. So what is negative 4 over 2? That's negative 2. Square that, gives you 4. But because you're adding 4 into the expression, that would totally change everything, right? So that we don't change that, we're going to subtract by 4. That way we're compensating for adding that 4. And then now we still have the same thing. Since this is a perfect square, you're going to be able to factor out x minus 2 squared, and then combine these two, gives you positive 3. And there you go. You can write it this way, right? You can always write any number you want. You can always write it as a perfect square. How? Just take the square root of it and then square it, right? So this is the base of this square. So that's not never going to be a problem, right? So what we're going to do now is we're going to go ahead and take the integral of this. We're going to rewrite it as a sum of squares. When you have a sum of squares on the denominator, That means we're going to be using arctangent. Here, a will be the square root of 3, and u will be x minus 2. So we're going to have 1 over a, arctangent, u over a. So it'll be u over a, and then plus c. And there you go. Alright, so I encourage you guys to try this one on your own. Let me know if you have any questions on that. And then, so we have basic integration rules now, right? We're going to summarize the integration rules. We already know these are the basics. We have the constant times the function. You can factor the constant. When you have u by itself, you just add u. The natural log, right? When you have 1 over u. When the power, the integration for exponentials. When you have addition of two integrals, the power rule, the exponential rule, the trig functions, and we have a few more. Then more integrations, and then finally we just added a new set of integrations. Again, we're not saying that you're integrating inverse functions. You're not integrating inverse functions. We're saying that the end result will be an inverse function. Okay. All right, so the last example here is going to be very important for us to kind of put everything together. And I sort of mentioned already this before, right? But I hope that this sort of makes sense. Why are we doing this? So this example is asking us to compare integration problems. Find as many following integrals as you can using the formulas and techniques you have studied in so far. So in the first one, it's asking us to take the integral of 1 over x times the square root of x squared minus 1. Well, I see a square root, I see difference of squares, right? Because 1 is always a square. And I see the x on the outside. So this suggests that this is going to be one of the rules, right? And I can see this rule number 20. So if I let u equal x and then a equal 1, right? Because this is always 1 square. Then following the formula, right? If it checks out everything, right? If you guys notice, you have u square and then u, right? You have x square and then x, and then minus a perfect square, So a is going to be 1 over 1 arcsecant u over a, so x over a plus c, and then that gives us, by simplifying, arcsecant of absolute value of x plus c. Perfect, right? That makes sense. Now, why? Now we're going to try the next one. But if you guys notice, on this example, you were not able to do anything else but using the arcsecant. If you notice over here, now if I add as x here, then I can't use this one anymore. If I had the x there, now this gives me a different approach, right? Just by adding the x on top, this allows me to actually use the u substitution and then use the power rule. As you guys will see here, if you let the radicand be x squared minus 1, the derivative of this will be dx 2x dx. Then we're going to ask ourselves, okay, that's cool. I see that this is going to be my u, but I'm still missing my du, right? I'm missing my du. Well, du needs to be 2 times x times dx. I have the x, I have the dx, but I'm missing the 2, so I compensated for missing the 2 by multiplying by 2 and dividing by 2. This is du, so that's going to be your du. This is going to be u, so u is going to be on with the square root power, so it'll be u to the 1/2. The 1/2 always carries, it's always carry over. And then now we have the 1/2 times the integral. I'll move this to the top. You have u to the negative 1/2 times du. By using power rule, then we can integrate this by adding 1. It gives you positive 1/2, and then divided by a new power. When you divide by a fraction, you can multiply by the reciprocal. Replace u back in terms of x, which is x squared minus 1. Then take the square root of that, right? These will cancel each other out, and then it gives you this. So there you go, right? In this case, we had to use U substitution and the power rule. And the last one, we actually had to use the arcsecant rule. And then the last one here is asking us to do the antiderivative of this. Now, if you notice, we would have to actually go back to the top. And it seems like it's going to work, right? Because you have a square and you have a square inside the square root. So it seems like it's going to work. But in this case, if you notice, x squared is positive and the constant is negative. So this one is not going to work because the constant is positive and the variable is negative. So that one's backwards. And then this one, it seems like this could work, but even this one, you're missing a u in front of it. This is not going to work because obviously for many reasons you don't have the square root and you have a plus. So therefore, this does not work for any of the rules that we have. Does not match any of the formulas or substitution, so we cannot integrate this problem with any of the techniques discussed previously. So this one cannot be integrated with the techniques that we know so far. Alright, so a brief review of this is the whole point of this is that now we know how to integrate another type of functions, and the end result will be an antiderivative that involves with inverse functions. Okay, so I hope that this makes sense. Please let me know if you have any questions. Make sure you guys read the book, read the textbook, read the notes, review, and don't hesitate to reach out. Thank you.